Okay, well, welcome back from Thanksgiving. I hope it was good. Hope yours was as good as mine. But always too short. Okay. So, and unfortunately, I gave you all this work to do over the holidays, huh? I mean, don't we have an assignment due today?
Yeah.
And I confess I did not look it over before I came to class this morning, and so I'm not sure. What was due today, A19 or A20? A20. I just gave back A19. So A20, well, I think it was to prove, according to my notes here.
It was 11.6, 11.7a, like the exercises, and then prove 11.4.2 and 11.7.
Okay, so 11 point, the proofs from the equation sheet are 11.4.2. E is an element of the empty set equivalent is false, right? And the other one, any questions about how to do that? I think it's pretty straightforward. You start with the left-hand side. Any questions about how to do that? There's only one thing you can use, right? An element definition of an element of, right? Are you with me? And then 11.4.1. What does it mean? What is the empty set? And then so, yeah. Is that, I think. Are we good? Then the other one was 11.7. Oh, it's another x is an element of. Oh, you want to look at the exercises?
I did 920.
I have no idea. I forgot last step.
Which one was the last one?
Which are you talking about? Exercise 11.7.
That's the last one you gave us.
So we have some conversations going on among the students here. For those of you who are watching.
9.2 twice. 9 point rule twice. Then it takes substitution.
Rochelle, are you asking about 11.7?
A, like the exercise. Because you
It's
gave
kind
us
of
the steps
it was
for
an
most of
ugly
them,
proof.
but after
11.7a is B. 11.7a is you have to prove B. You have to prove that B equals set B equals set C equivales B equals C. Is that right? What you have to prove? And you start with the left-hand side?
yeah.
And what does it mean for two sets to be equal? So you use, so what does it mean for two sets to be equal? Which one do we use here? 11.4. Is that how you did it?
Well, you gave us the steps you wanted us to use this weekend.
Oh, I gave you the steps on the
Yeah,
webpage.
I just, where you left us, you had us do 11.2 and then 11.5.1. So you didn't have us start at 11.4. But where you left us, because we ended with 8:15, where you left, I just didn't know where to go from there because it was a bigger mess than what we started with. So,
Oh.
but they figured it out, so they helped.
Oh, so you got help?
Yeah.
All right. Well, unfortunately, for those of you who are watching this, some of the students have helped each other. And
Plagiarism.
you'll have to come to me for help, I guess. Well, is that it? Are there any more questions about the homework assignment that's due today? Are we good? Oh, you're actually going to hand it in at class. That's impressive.
Every single time.
Sure.
Thank you.
You ready to hand yours in?
I've asked you about next class.
Okay. All right. Well, if there's no more questions, let's continue on. Now, there's going to be A21, there's going to be, 1, 2, 3, 4, 5. This next assignment is going to be pretty hefty. Every once in a while we have a pretty hefty assignment where you have to do a whole bunch of proofs. And that's what's going to happen with this next set. So at the end of the class last time, we were talking about 11.7. All right, and this 11.7, we gave an example of 11.7 where R is the characteristic predicate of the set. It's called the characteristic predicate of the set. And what happens is this expression, X is an element of some set, that's a Boolean, right? And R, the range is always a Boolean. And it turns out that X is an element of the set X, range R. And of course, the abbreviation, that's an abbreviation for body X, yeah? That is R. And I wanted to show you last time we showed that if X, let's take a look at 11.7. What is this X on the very left-hand side? Is that bound or free?
Free.
It's free. And if X is on the right-hand side, the expression R, on the right-hand side of the equivalence, if X is in that R, is it bound or free?
Free.
It's also free, right? But if X, what about the X inside the R that is in the set comprehension? Is the X in that R bound or free? That's bound. So it's a different X from the X that's in this R. So what I did in 11.7.1 is I just changed the dummies to make it more clear. So here's the point. 11.7 is a theorem. Okay? And anytime you have a theorem, you can always do textual substitution on a variable, right? Are you with me? Okay, so you can do textual substitution on variable X. So you can do textual substitution on variable X, right? So I'm going to do textual substitution on variable X. So the theorem is X is an element of set over X, range R, equivales R. This whole thing, we're going to do textual substitution on this whole thing. And what we're going to do is X replaced by Y. Now here's my question. When we say this equals by textual substitution, my question is, where does this textual substitution take place? It takes place on this X, and it takes place on the X that's inside this R. But does everybody understand that it doesn't take place in here? Because this X is bound to this X, right? So by textual substitution, so let's do the textual substitution. X with X replaced by Y is just what? Y. So this is the same thing as Y is an element of a set of all X, R, equivales what? R with X replaced by Y. So and that's 11.7.1. So this is 11.7.1. So that's the meaning of it. Okay. This is always a little confusing one to use because, using that, I mean, you have to keep it clear in your mind what is, what the fact that the X in this R is bound to this X, but the X in this R is not. It's free. So here's an example. Give you an example of this. Suppose we say Y is an element of the set of all X, range 0 less than or equal to X less than 5. 0 less than or equal to X less than 5. Now, what does that equivale? by 11.7.1. Here, just as an example, what does this equivalent? Mason, what do you think it equivalents? By 11.7. Y is an element of the set X, range 0 less than or equal to X less than 5. What does that equivalent by 11.7.1? But, so what do I write down here? To what? Yeah, it's... Yes, this is less than or equal to 0, less than or equal to Y, less than 5. Does everybody see that? Okay, in other words, Y is an element of this set. Well, what is this the set of? It's a set of all X, 0 less than or equal to... So what is this set? But if we were to enumerate this thing all out, what would it be?
1, 2, 3, 4.
Yeah, this would be... Yeah, this would be Y is an element of the set 0. I guess it includes 0, huh? So 0, 1, 2, 3, 2, 3, 4. Well, that's the same thing as 0 is less than or equal to Y is less than 5, right? This is true exactly when this is true, and vice versa. Yeah? Okay. So, in summary, all these three things are equivalent. Summary. These are all equivalent. These are all equivalent. These three things. Let's say capital S is the set S equals the set 3, 5, okay? And furthermore, S equals the set of X, range X equals 3 or X equals 5, okay? So here this is enumeration, here this is comprehension, but another thing is X is an element of S equivales X equals 3 or X equals 5. You see, all these three things are equivalent. And this right here, this expression is called the characteristic predicate. See, like it says there. R, does it say? Yeah, R is the characteristic predicate of the set. This is the characteristic predicate. This is the characteristic predicate. Okay, the predicate is a function that returns true Boolean, type Boolean, right? And this is either true. This is like if you consider this to be a function of one variable x, it's a function that returns type Boolean. It's either true or false. Either x is in this, you know. Either this is true or it's not, depending on the value of x. All right. So that's the idea behind the characteristic predicate. Okay, let's go on now. 11.9, oh gee, what does 11.9 say? It says X, the set over X range Q equals a set over X range R is equivalent to what? Equivales what? For all X, Q equivales R. Well, that's kind of obvious, isn't it? The only way those two sets can be equal is if for all X, Q equals R. You know, if Q is true, R is true. If Q is false, R is false. Right? Okay, any questions about that? And what about the next one, 11.10? X is an element, the set over X range Q equals a set over X range R is valid if and only if Q equals R is valid. Well, I think that's pretty obvious, yeah, because we talked about validity, didn't we? Implicit universal quantification, remember? Remember that phrase? Implicit universal quantification. Something is a theorem if and only if something, what was that? Do you remember what this is? Yeah, what was that? It was, oh, let's find that.
Range true. There's a, go back. Use the theorem. Yeah, there we go. Well, actually,
for all X range are true equivalence true? Yeah. No, and 9.16. P is a, yeah, it's 9.16 is what I was thinking of. P is a theorem if and only if for all X range P is, so that's an example of that. All right. So that was 11.10, okay? And now 11.11 is a little summary of methods for proving set equality. I want to comment about these. Use Leibniz directly. That's just very rare. Let's not even think too much about that one. B, however, is crucial. Now, you remember from was it last lecture that we did the 9.8 lemma? Is that where we did the 9.8 lemma? Do you remember that?
Yeah.
I think that was that. Now, that was really important. This we're going to use all the time. So 11.11b, you might want to note that on your equation sheet. That's the important one. It says use axiom extensionality 11.4 and prove the 9.8 lemma. And the way you set up your proof for that is you say, let V be an arbitrary element and prove that V is an element of S equals V is an element of T. And then we said, if you prove that lemma, then you don't have to do the second part of the proof, which is to go back and, plug it in, because that part of the proof would be the same for everyone. So why keep having to do the same thing over and over again, right? So that one is a real important one. And 11.11c, the third technique, is to show that this set equals this set, is all you have to do is show that Q equals R, okay? And that comes from 11.10. So that's the basis, 11.10 is the basis of a proof technique. And we'll do that one occasionally. But the one by far that's the most important is 11.11b. Okay. Now, the next set of theorems and axioms are introduce some operations, some binary infix operators, okay, and some other characteristics of a set. So let's take a look at 11.12 first. Axiom size. Now, you know this pound sign? This is kind of like an abbreviation in mathematics about, and the way you say this is the number of elements. What this means when you say pound S, you mean the size of S or the number of elements in S, okay? So what 11.12 is saying is, and it's an axiom, so we don't prove it, but it's the number of elements in S equals, now this is interesting, the sigma x. Now what is the operation for sigma? Plus. So we're adding, right? And the range is x is an element of S. But tell me, what's the body? 1?
So if X is
What are we adding? We're adding 1 plus 1 plus 1 every time.
that X is an element of S.
Ah! We're adding 1 plus 1 every time x is an element of S. Makes sense?
Yeah.
So for every element every time x is an element of S is true, that's one more, that's one more, that's one more. So you add up 1 plus 1 plus 1, and you're adding up however many elements there are in the set. Makes sense? Actually, you said it so well, I don't think I need to do an example.
Good.
But now, what about axiom subset? Now, we're starting some important ones now. You guys have done this before, right? Have you done subsets before? Venn diagrams? Okay, so we'll do them again. Yeah. So let's see. S, so here what we're saying is S is a subset of T. So let's let S be the set 0, 1, 2, 5, 8, and T be the set 0, 1, 2, 5, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, 120, 121, 1 0, 1, 2, 3, 5, 6, 8, 10. Right? And I'm claiming that S is a subset of T. So if you were to draw this on a Venn diagram, okay, so here's 0, 1, 2, 5, 8, 0, 1, 2, 5, 8. Okay, and so this is the universe. How do we decide to draw the universe? Like this? Right? So this represents the set S, and T represents the set 0, 1, 2, 5, 8, 0, 1, 2, 5, 8. But in addition, it includes what? 3 and 6 and 10, right? So maybe 3 is over here, 6 is over here, 10 is over here. So the T set would look like this, right? So what by definition, now we're not going to prove 11.13 because it's an axiom, so it's like the definition of what it means to be a subset. It says for all x in the range, x is an element of S. Well, what is that range x is an element of S?
All the elements of this.
Yeah, so that's 0, 1, 2, 5, 8. So the x, that set of x is 0. So is it true that 0 is an element of T, and 1 is an element of T, and 2 is an element of T, and 5 is an element, and 8 is an element of T? Yeah, so therefore S is a subset of T. Now, the next one says S is a proper subset of T. So we know that S is a subset of T. Equivalence true. What about S is a proper subset of T? What does it have to be in order to be a proper subset?
Not equal to T. It has to be a subset.
It has to be a
It can't
subset,
be equal.
but it can't be equal to it. Now, is this also true?
No. Yes.
This is also true, right? And we know that T does not equal S, right? So therefore, S, in this case, S is a proper subset of T also. You know what? This is very similar. You know, they chose these symbols to be very similar to less than or equal to and less than, you know. Because what does it mean to be less than? It means it's less than or equal to, but not equal to. You know what I mean? So that's a good analogy to use. And then, of course, you can just flip it and go the other way. Superset, T is a superset of S, just means S is a subset of T. And T as a proper superset of S is the same thing as S is a proper subset of T. All right, so 15 and 16 are, it's just like, you know, that's just like this is implies, this is follows from. Sometimes you just want to write it the other way around. Okay?
Is the implicit a subset of S?
I think we're going to have a theorem that the empty set is a subset of any set. Do we have that?
Yeah.
Is that coming up?
Probably. It should.
I don't remember if it was or
Maybe it's not.
not. Well, the identity.
When we prove it, maybe.
I would have thought that we would have had a theorem that says that the empty set, man, look at all these
Oh,
theorems.
yeah, go back.
Yeah.
One more. It's right there. 11.6.
Oh yeah, the empty set is a subset of S. Yeah, it is a theorem. Okay? All right, so let me see, what else do we have? So proper superset, complement. Now let's take a look at the complement. Okay, so the complement is 11.17. Again, that's an axiom. Now, let's suppose that the universe is this set. Let's say it's the set A, B, C, D, E. Okay, let's just define that to be our universe. Okay, so, and let's let S be the set B, D. right? Then V is an element of the complement of S equivales V is in the universe and V is not an element of S. So what elements are in the universe that are not in this? In other words, what is the complement of set S? This is,
All the other letters,
which is
A, C, E.
A, C, and E. Is this marker dark enough? Yeah. So the complement of S would be ACE. Does everybody see how that works? And you know how this looks like, you know what this looks like in a diagram, in a Venn diagram? If this is S and if this is U, then the elements that are in the complement of S are all the elements that are here. Everybody see
Why
what?
is it not like a quantification, like for all elements?
Why is it not a Well, I mean, ultimately,
Why do you need the V as an element of for each of them? Why could you drop the V as an element of and just have the complement of S equals the universe and not?
ha, because then you, yeah, the good question. Because you can't do the and between two sets.
Yeah.
Are you with me? That's a really
You could
good
do the
question.
and between like a quantification though.
You can do an and between a conjugation,
Why
but
don't
you can't do an
Why don't
and.
you make them? Oh, because then.
Yeah, now that's a
You wouldn't need
really,
to add, because then the quantification would be a theorem as well.
yeah. And that brings up a really, really good point, you guys. I mean, to keep all of this stuff straight, you really should always ask yourself about the types. Because in 11.7, these are equivales between two Boolean expressions. Are you with me? And so if you drop the V as an element of, you would have the complement of S. But then you can't say the universe
Set
equal the universe and, you know, not, well, anyway, it wouldn't make sense. So anyway, yeah, that's how we have to do it, to keep the types straight. And then 11.18 is a theorem. It says V is an element of the complement of S is the same thing as V is not an element of S. And you should be able to prove that. In fact, is that one of the ones? No, I guess I didn't ask you to prove it. But it would be a nice one to prove. I think it would be pretty straightforward, I would hope. How would you prove that? V is an element of the complement of S. You start with the left-hand side, right?
We're gonna do it.
Well, it's a one-stepper, right? You start with the left-hand side. V is an element of the complement of S. And what would you do? 11 point what? 11.17, that'd be V is an element of U and V is not an element of S. But then we said for V is an element of U is true, so true and then true and, yeah? Okay. Oh, and what about 11.19? Complement of S is S. How would you prove that? How would you prove, now here, this is, two sets are equal. So how would you prove that?
Double complement.
No, that's what we're trying to prove. That's what we're trying to prove.
9.8.
Prove the 9.8 limit. Say what?
V
Let-
is an arbitrary variable.
Let V be an arbitrary element
V is
and prove that V is an element of
S.
complement of S equals V is an element of S. So what is V as an element of the complement of S? What would that be? No. By what? How?
So complement, this is like our
V-
double negation theorem.
Well, yeah, but how? But you would have V is an element of the complement of S. So then what would you use?
11.18.
11.
S replaced by complement of S.
Yeah. 11.18. Yeah. And then that would be. But then you would have V is not an element of the complement of S. So then what would you do?
Do it again.
Do it again.
Well, but you have not is not an element. So what does the not? What does the slash thing do? Remember what? Remember, anytime you have a slash between an operator. This is important. How about this? Maybe we should prove this. Here, yeah. Let's prove this. Here. Let's say 11.19. 11.19 proof. Okay. So let's start. So here's what we'll do. We'll prove the 9.8 lemma. And what do we always say? Let what?
Let V
Let V be a what?
independent or an arbitrary element.
Let V be an arbitrary element. And then show that what? And prove what? Prove what?
V is an element of
V is an element of what?
complement
S
equals
equals or equivales, right?
V is an element of
V is an element of S. So let's start with the left-hand side. V is an element of complement S equals by, what did you say to use? What were we going to use? 1118. So now what is this? V is what?
not an element.
Not an element of what?
Complement
Complement of S. But now what, my question is, what does this not an element of do? How do we do this?
You'd say not V is an element of.
Yeah, how do we do this?
V is an element of not S.
No. Remember here,
Not V is an element of.
here we're going to have to go all the way back. We're going to have to go all
Like you pull it out in parentheses, right?
Yeah.
So it's not
Look.
is an element of S.
Oh shoot, it's not on my slides.
It's okay, we got it.
Is it in your
What is element?
is it in your equation sheet? How with these
It showed
how with these operators, there's a footnote. Is it on the equation sheet?
Oh, yeah, operators on lines.
It
J,
says
L, and M,
all-
slash through them to
Yeah.
denote negation.
Operators on lines J, L, and M may have a slash through them to denote negation. For example, B is not equivalency is an abbreviation for blah, blah, blah. So the way you do this is you say equals by definition,
Definition of not.
yeah, definition of not an element of, that's not V is an element of this.
Again,
Are you with me? Is everybody clear on that? Yeah, sorry I don't have that on my slides, but it's on your handout, that fact. Is everybody clear on this? Okay, now, and then this equals by what? Huh? Equals by what?
1118.
1118 again. Whoops.
Not V is an element of
Yeah.
V is not an element of
Not, V is not an element of S, but this equals by definition of not an element of, not V is an element of S, which equals by what? Etc.
Done.
Double negation, V is an element of S. Done. Boom, right? Are we good?
Yep.
Okay, so that's, yeah, remember this. And by the way, this slash thing is going to come up in a lot of subsequent theorems as well. In fact, it came up here even. S is not an element of T, right? Okay, so the complement of the complement of a set is a set. Now, the next axiom is axiom union. So what does it mean to take the union of two sets? Okay, so let's do this. Let's let the universe. Let's have the universe be A, B, C, D, E, F, and let's have S be A, C, E, and let's have T be B, C, E, F. Now my question is, now let's take a look at each one of these. Axiom union. So V is now it's defined with V is an element of S union T. So what does it mean what is the definition of S union T? V is an element of S union T if and only if what?
V is an element of S.
Or V is an element of T. So tell me, what is S in this particular example? Now, unfortunately, union is not the universe, and it's also not U, S-T-U-V. So S, what is S union T? What set is that?
A, B, C, E, F.
Yeah, A, B, C, E, F. And then the next one is intersection, so that's S intersection T. And what is the definition of intersection? V is an element of S intersection T if and only if V is an element of S and V is an element of T. So which ones are in both?
Set.
C, E, is that right? Is that right?
Yeah.
And what about the set difference? Have you guys done set difference? This might be one that you're not familiar with. What is
An
it?
S and not G.
Yeah, okay, so now which ones of this universe are not in T?
Why do we care?
Wait. It's an element of S and V is not in T.
So it's the ones in S that aren't in T, which is A.
Yeah, so is that A? It's the ones in S that are not in T. The ones that are in T are C and E. So you're right. So it's A. Are we good? Okay, and now let's do a little Venn diagram picture of each one of these. So if this is U,
Wait, is T supposed to be
B, C, E, F.
Why is,
Are we good?
I just understood that C was
Now, see, the set difference might be one that you're not quite familiar with. So here, if this, so now let's do this. If this is S, so in each of these cases, this is S and this is T. This is S, this is T. This is S, this is T. Now, in each one of these cases, let's shade in what the union and intersection and set difference is. All right, so here let's do, this one let's do S union T, S intersection T, and S minus T, set difference T. So what are the elements in S union T? They're the ones that are in S or in T. So which ones? These, including this, including the ones that are in both, are you with me? And including this. Does everybody see that? Whereas S intersection T, that's the elements that are in S and in T. So that's this one. Are you with me? But now what about this one, S minus T? Those are the ones that are what? In S, but what? Not in T. So what is this one? This is like it's this one, but not all of S. It's not this. Is everybody, are you with me on that? Here's a little picture of S minus T. Yeah? Are we good? And now there's one more interesting set before we summarize this, and this is the power set. Now this is a really interesting set.
Power set.
Power. Check this out. Suppose S is the set A, B, C. Now, I ask you, sports fans, let's take a look at this. Now watch, you can draw some really interesting conclusions by just looking at 11.23. It says V is an element of the power set of S. If and only if what? V is a what? subset of S. Wait a minute. V, I thought this is V is an element of. What's the type of V? How can V be a what? Hey,
This is a variable and a set.
yeah, how can it be a set? Because in order for V to be a subset of S,
A one variable.
V must be a what?
One.
Now what must its type be? In order for V to be a subset of S, what must the type of V be? It must be a set.
Yes.
It has to be a one.
But wait, it must be a set. But that means that this power, that means P of S must be a what? What must it be? What must its type be? Because if V is if we have a set is an element of some other set, that other set must be a what? No, more than that.
Dang it.
No, more than, but its type. What must its type be? No, come on. If V is going to be a set, but it's going to be, we know that V is a set by this right-hand side, right? Are you with me? Here, look, you guys. We know.
Then it has to be in a set of sets.
That's what it must be. The power set must be a set of sets.
That's lame.
No, we can deduce that from here. Are you with me? It must be a set of sets. So if S is the set ABC, my question is, what is PS? What is the power set? It must be a what?
Figure. I know it's.
No, it must be,
It's like
if,
two sets.
A set.
well, it's a set of sets. So here's the set. And now instead of these elements being like ABC, what are they going to be?
S.
They're going to be sets. Now my question is, what are the sets that are in there? What does this say?
S. S.
V.
No. V.
S.
These are element of.
No, I'm talking about in terms of ABC. What is this set? This is a set. This is a set of what? This is a set of blah, blah, blah. A set, blah, blah, blah. Another set, blah, blah, blah. You understand what I'm saying? These are going to be, the elements in this set are going to be sets. My question is, tell me what those sets are.
S.
Set of
A,
A.
B, and C.
Well, let's start with the short. So what's the smallest one? No, there's one smaller than that. Empty set. Okay, the empty set. What's the next biggest one? The set A. Are you with me?
Set B.
Set B.
So just a bunch of one variable sets.
Set C. No, because now is the empty set a subset of it? Is A a subset of this? Is B a subset? Is C a subset? What else is a subset of this?
Set AB.
A, B.
Set AB.
Set AC.
Set BC.
Set BC.
Set ABC.
ABC.
Set A, B, C, inset into the set. Are you with me, sports fans? Are we good? Now look. Does everybody get this? Now look, here's table 11.1. And what it does is it's an example of all of these binary infix operators, union, intersection, set difference. We have this prefix operator, complement, and it gives examples and it gives the type of the result, okay? So let's take a look. The first line, we have the empty set, the universe, and some variable, right? Okay, so an example is the empty set, the universal set, or S. The type of the result, the type of the empty set or the type of S is type set T, all right? And then we have set enumeration, and we have each one of those E1s, E2s, E sub n, if that's of type T, then the set enumeration is of type set T. And we have for comprehension, they're type set T, set T. Set membership, X of type T is an element of S of type set T. That's a Boolean, right? It's either true or false. Either X is in the set or it's not. Either X is in S or it's not. It's either true or false, right? It's either, so that's type Boolean. Set equality, that's type Boolean. If we have one set S equals another set T, either those two things are equal or they're not. So that's a type Boolean. Set size, pound S, type set T, that's a what? natural number. There's either no elements in it, or there's 1, or there's 2, or there's 3. Are you with me? So that returns the type. So that pound function returns type. It's not a predicate, right? Because it returns a natural number. It doesn't return a Boolean. And then if it's a proper subset or a proper supersub or a proper superset or a subset or a superset, if S is one of those, is a subset of T, that's either it is or it's not. So that's type Boolean, right? The complement of a set is a set. Its type is a set. Intersection, union, and set difference, those return a type set. And check this out. The power set, right? The power set where S is of type set T is a set T. So it's a set of sets.
That's exciting.
Are you with me, sports fans? Is that something? And we got all of that out of just looking at the types of this 11.23. Of course, that's an axiom. We don't prove it. All right? All right. So next time we will start in with a great meta theorem, and we'll have, this will be the basis of a proof technique that we can use for our. How long have you taught this class?
How long have I taught this class?
Seems like forever. Actually, there's a nice little story with that. I used the manuscript of the book before it came out because I was at a workshop with David Grease, and when he was writing the book, and it had not yet been published, and I was very interested in it, and he gave me a copy of the manuscript, so I used his pre-publication manuscript. So when was the book published? Do you have the? Yeah, we can actually tell how long because of that. By that, the first.
Were you teaching this class before he published it, or before he came up with the manuscript?
Well, I mean, the class was taught a lot differently because this book is very unique. Say it again. When was it published?
93 actually.
93. So, probably 92. So how long is that?
18 years.
Yeah.
I'm
But
still so excited for this material.
I tell you, I'm excited because this material, in my opinion, this is a landmark book, and if I had my way, all of computer science theory would be taught based on this equational system of logic. It's that good. So I'm here to lead the charge. Okay, anyway, see you next time.